Algorithmic homology.
Thanks very much. Okay, so I'm going to tell you about the quantum complexity of Clique homology. So this is going to work with Tamara, who's also here this week, I think. Okay. So homology is a branch of topology which studies holes in spaces. And today I'm going to try to convince you that homology has some quantum mechanical structure to it. And this structure will let us find a problem in homology, which is phrased completely in the language of topology, which turns out to be characterized by quantum complexity classes. So this is a computational statement that there is quantum mechanical structure in this homology setting. So the problem will be given a description of a discrete space G. I call it G because the input will be a graph, and a dimension K. The task is to decide if, in the yes case, G has a k-dimensional hole, or in the no case, G is far from having a k-dimensional hole with an appropriate notion of far. And we'll find that this problem is contained in QMA and is QMA1 hard, where QMA1 is a perfect completeness version of QMA. And for the purpose of this talk, just try to think of them as not too far away from each other. They're kind of the same thing. Okay. So before I dive in, let's talk about some motivation for why this is a cool result. So there's lots of papers from the last 5 years which study these quantum algorithms for topological data analysis. And you can see a few here. And a big question is sort of, when you have a quantum algorithm for a classical problem in data analysis or machine learning, it's like, can you dequantize this algorithm? Because a lot of them sort of were dequantized in after writing them down. So if we find that there is really something quantum going on in the problem, that sort of can give us evidence that there is reason to believe that these quantum algorithms are doing something non-classical and we cannot dequantize them. So this is sort of an algorithmic implication. Okay, and yeah, zooming out more generally, we like it when we find classical problems with quantum mechanical structure. So here's just a few examples. The hidden subgroup problem, which is sort of the main driving force behind Shor's algorithm, you can relate it to the quantum Fourier transform, like position and momentum. So you sort of see quantum mechanics in the problem. And similarly, there was a story in the 2000s with this Jones polynomial, which turned out to be, BQP complete. And the quantum structure in this sort of knots invariant came ultimately from topological quantum field theory. And today I'm going to try and convince you that there's a similar story with homology, where the quantum mechanical structure in homology comes from a branch of quantum mechanics called supersymmetry. Okay. So how are we going to specify? I said at the beginning that the input to the problem is going to be a description of a discrete space. How are we going to specify the space? And this will come from what people do in this classical field of topological data analysis. So you can imagine having like a data set, maybe some points in space, and you're wondering about the topology of this data set. So how could you define such a thing? So what you could do is you could pick like a length scale epsilon and then create a graph where you connect 2 points if they are within epsilon. So that gives you a graph. But a graph is still not really a topological object because it's still, if you're an ant on a graph, you can only move in one way. So you sort of want to build a discrete manifold, like a high dimensional sort of thing that has topology. So you can do that by, from the graph, building its clique complex, which is a simplicial complex. And how you do that is every time you see a clique in the graph, so if I see, for example, a triangle, I fill it in. So a triangle becomes like a sort of 2D solid thing. If I see a 4 clique, I sort of fill it up with water or something, and it becomes a solid tetrahedron. And from this, I get like a so-called simplicial complex, which consists of vertices, edges, triangles, tetrahedra, and higher dimensional versions of these edges. Okay, so here's my one slide crash course in homology. So we're going to try and make it through this. So if I give you one of these simplicial complex objects, maybe I'll give you a graph and you build it simplicial complex. How can you ask about what are the holes in the various dimensions in this space? Like how can you mathematically define such a thing? So the first step is to take the k-dimensional simplices. So like if k equals 2, for example, this would be the triangles in the simplicial complex, and define a vector space, which is a complex vector space, and it's going to be spanned by these simplices. So each one is a computational basis state in this so-called chain space, Ck, and they're indexed by the dimension. And then you may have seen this in various contexts, for example, in error correction, et cetera, where you have a sequence of these spaces with these so-called boundary maps going between them, going down in dimension. So these are linear maps just connecting these spaces. And how do they act? They act very intuitively. If you can define their action by how they act on the basis, and they just take a simplex and output whatever its boundary is in the dimension lower. So if I input a triangle, I get the sort of superposition of the edges that go around the triangle. Or if I input an edge and I take its boundary, I'll get like this vertex minus this vertex in the vector space of one dimension lower.
So this way, you define you put a qubit on each triangle, edge, tetrahedron.
We haven't talked about qubits yet. This is just a vector space where the basis is the, so like C1, the basis will be the edges.
Oh, I see.
C2, the basis will be the triangles. C3, the basis is the tetrahedra. Okay, so a very deep fact about the universe is that if you take a boundary twice, you get 0, right? So if I sort of take this blob and I take its boundary, I get the surface, but that has no perimeter. Or if I take a disk and I take its boundary, I get the perimeter of the disk, and that has no endpoints, right? Yes. Right. Okay. So these things also have an orientation by convention, and it's really just a convention. So it's like defining, like the edge this way is like minus the edge going the other way. Yes. Yep.
So are you going to be using over Z2 or in general?
Yeah. So good question. So if you do error correction, often these things are defined over the binary field, but here we're going to use the field of complex numbers. Yep.
The sign is important for the boundary to go to 0.
Yeah, that's right. So over Z2, the -1 is +1, so it doesn't come up in that context. But in general, you want to like keep track of the orientation of everything. Yeah. So for example, if I take the boundary of this thing, it has an inside and outside, and then it would be like a normal vector on the surface. For example, that would be like how it would work in that dimension. Okay, so the boundary of the boundary is 0. That tells me that the image of the boundary map from above is contained in the kernel of the one going one lower, right? That's just tautological. But are they equal? And we define the holes in the space to be the extent to which those two things are not equal. So we define the k-dimensional holes to be the things that have no boundary, yet which are not the boundary of anything. So why does that make sense? So if we see this picture of a torus here, if I imagine a loop which lives, just a small one that lives on the surface, so that has no endpoints, right? So it has no boundary, but it's the boundary of the disk inside it. So it appears in both thing kernel and the image, so it gets killed. But this red loop and this purple loop here, they have no endpoints, but they're not the boundary of any two-dimensional plane. So those will survive this quotienting, and those appear as holes in the space. So this is why this is the correct definition of k-dimensional holes. Okay, so that's the crash course in what we mean by holes in spaces. Okay. Yeah. Any questions as well? I know this is it's a lot to sort of. This stuff is scary for us, but it's really not too interested yet.
So according to this previous discussion, that shape has two holes?
Yes, so H1 will be C2 in this case. It will be a two-dimensional vector space. Yeah. These things are all vector spaces, so you ask about like it has two holes, it means it's two-dimensional.
What about the dimension of these different spaces? So you can make a general comment like when they equal or when they're not equal as a vector spaces.
Which ones? The chain spaces?
Different case.
Right. So yeah, we'll see this later, but the dimension of the kth chain space is the number of k-simplices, right? Because each one is a basis vector.
So that algorithm to create the object from points. So what are the input parameters? Just epsilon, or are there more parameters?
Right. So we'll actually, yeah. So this is going back to how do we specify the space. So we'll actually, the input will be a graph. So we'll sort of forget the fact that the graph came from a metric space with data points, and we'll just say the input's a graph, and then that defines the simplicial complex via this turning cliques into simplices procedure.
And so the second step, it doesn't depend on epsilon.
No. Yeah, it's completely combinatorial. Yeah. Okay. So now that we know what homology means, we can ask a computational question. So given a graph, decide if it has a k-dimensional hole or not. So we can ask, what is the computational complexity of this problem? And the first observation is that it's not obviously inside NP even. Okay, so now why is that? It's because how would I prove to you that there's a k-dimensional hole in this graph? I would have to give you the element of this thing that's not in here, right? That would be a proof. But these things live in this CK vector space. Now the CK vector space is the span of the k-simplices. How many of those are there? What is the dimension of this space? Well, the k-simplices are the k+1 cliques in the graph, right? There's an indexing thing where triangles have three, but it's a two-dimensional triangle. So how many of those are there? There could be as many as something like n choose k+1, right? So if k is growing with n, this could be exponential in the size of the graph. So we see that from this small graph, if we ask about the homology, there emerges an exponentially large vector space. So this is sort of the first place where you start to see quantum mechanics start to appear, because it's similar to when you have a small number of qubits, and if you ask about it, then you have to look in this very big Hilbert space.
For constant k?
So for constant k, yeah, so that's it.
Still possibly be in NP.
So yeah, so we allow k to grow. Yeah, I think it possibly would be. But then, yeah, so you have to then ask, what about all of these algorithmic speedups you get? And then I think the exponential speedups will turn into large polynomial speedups if you have k equals like 20 or something.
But is it in NP then?
It would be, I mean, the witness would be of size n to the k. Yeah.
You have to also show it's not in the other.
Not in what, sorry?
Sort of in the image, but not in the kernel, or the other way around.
Oh, yeah, you'd have to work out how to actually check this, I guess. I think it would be possible. Right.
So would that be just linear algebra?
Yeah, I think so. I think it would just be linear algebra over a space of dimension n to the k. Okay, so this problem is not obviously inside NP if we allow K to be arbitrary. Okay, so we want to make this link to quantum mechanics stronger, right? So we have this chain space in which the homology lives, which is exponential dimensional. The next thing we'll do is we'll define an operator, which we call the Laplacian, which is a self-adjoint operator on this vector space, such that it's going to be positive semi-definite, and the ground space is isomorphic to the homology. So this thing has a zero eigenvector if and only if there's a hole in the space. And now this is really looking quantum mechanical because we have a large vector space with a self-adjoint operator whose ground space encodes the answer to our question about homology. And this thing is a sparse matrix, and we get sort of efficient access to it if we are given the graph which describes the space.
So Laplacian you can access any entry of the matrix from the graph.
It's the standard model of, I guess, sparse access, where you query a row and you get the entries of the row.
And you know which entries are non-zero answer.
Yeah, yeah. Everything you want about, you get it from just looking at the graph itself. So, yes. Yeah, so the graph is a small object. This Laplacian is like an exponentially large matrix, but the graph gives you access to it. And the Laplacian ground space is the answer to our question about how many holes the space has. Right, so what is this Laplacian object? I'm just going to sort of show you a bit of math to tell you what it is. So remember we had these boundary maps, which were linear maps which moved you down a dimension. So it's going to have two terms. It's going to have you can read it there. So the adjoint, right, will move back up. So the first term sort of goes down a dimension and then back up, and the second term goes up a dimension and then back down. So this statement that the kernel is isomorphic to the homology, we can just see a very brief proof of this by imagining sandwiching this self-adjoint operator by the state. You can see that you sort of get this, right? If you imagine sandwiching the left and the first and second term by a state. I should have mentioned like this Laplacian is manifestly self-adjoint and PSD. In fact, each term is manifestly PSD because it's a matrix times its adjoint. Okay, so we get these two terms. So if this is zero, if we want this to be zero, it means both of these terms individually have to be zero. What does the first term being zero mean? It means I'm in the kernel of the boundary map, right? What does the second term being zero mean? It means I'm orthogonal to the image of the one from above. So that's how it picks out an element in this quotient space. It says I'm the element of the kernel which is orthogonal to the thing that I'm quotienting. So I guess, why aren't they equal? They're not equal because the left-hand side is a subspace of the chain space, but this is some weird quotient thing. So what this is really saying is that for every equivalence class of the homology, there's a unique representative in the kernel. Okay, so with this sort of quantum mechanical structure uncovered, we can write down the problem which we actually study, which we'll call gapped Clique homology. So given a vertex-weighted graph, I'll maybe come back to the vertex-weighted at the end if we have time. Decide if it has a k-dimensional hull, or if it has no k-dimensional hull, and in that case, the minimum eigenvalue of this operator cannot be exponentially small. We ask for it to be at least polynomially small. So this is the sense in which it's appropriately far from having a hull.
How would a graph look like if it had exponentially small minimum eigenvalue?
Yeah, that's a great question. So, so this Laplacian, if I set k equal to 0, becomes the regular graph Laplacian. So then its minimum eigenvalue, you have this Cheeger inequality, right? Which tells you that if I'm a bottleneck, then I have a very small eigenvalue. So it's like almost disconnected, right? And if it's disconnected, then the eigenvalue, it will have a 0. So it's sort of, but I'm not sure there exists a Cheeger inequality for higher dimensions for this object, but that sort of intuition is like, if I have something that's almost a hole, then this operator should have a very small eigenvalue. I think that's the best thing I can say there.
So it's not about connectedness, it's about wholeness.
Yeah, so connectedness is the zero-dimensional homology, right? That's how many zero-dimensional holes is how many connecting components I have, right? And then 1 is how many loops, and then 2 is how many spheres, and et cetera. Okay. So this problem is inside QMA, and I'm claiming that's actually not hard at all. So what's the reason? The reason is because in the yes case, this Laplacian operator has a 0 eigenvalue. In the no case, it has an eigenvalue separated from 0. So I'm just going to ask for the element of the kernel of the Laplacian, and I'm going to run phase estimation on this Laplacian using the sparse access and check that its energy, if it's 0 or if it's above some threshold. So for that reason, this problem is inside QMA. That's sort of the easy.
You lose probability somehow. Like you because of the precision, I guess.
Oh, you're asking why there's a 1 here?
Why there's not a 1 in the first.
Oh, maybe there should be. But containment in QMA1 is a bit weird because it depends on the gate set and yeah. Okay, so I didn't think we looked at that too hard, but yeah.
So you started with points in space, and then that induced the graph by this closeness measure.
Oh yeah.
Is that restricted constant for graphs in it?
Yeah, that's a great question as well. So you're asking if every graph or if these graphs can be sort of realized by this topological data analysis. Yeah, I'm not sure, but also I think that a graph is also a sufficiently motivated classical input. So we can sort of start there in the pipeline. I'm not sure if the graphs in our construction can be realized as metric spaces. Was there a question over?
What? Yeah, high enough dimension, but maybe with some limited dimension.
Perhaps this is more appropriate towards the end, but is there like a maybe version of this problem that is in VQP?
Maybe, very possibly.
Say with more promises on the graph.
Yeah, I mean, so something you could do is you could, for example, embed something like the guided local Hamiltonian problem inside it, and maybe yeah, I think that could be. I mean, this is really the sort of uncovering the baseline, and then we can ask about algorithms for these objects going forward, and we can ask about their quantum complexity. Yeah. This is really the easiest thing to show that, to convince people that there's something quantum mechanical with this problem. Okay, so our result is that this problem is also QMA hard, QMA1 hard. Yeah, so that's the statement of the result. Yeah, the input size is the graph. So I give you the adjacency matrix of the graph. It's not like this graph is small. It's not like an exponentially large graph like we saw in, I think, in the previous talk, right? We were given Oracle access to a very big graph. The graph is really, I give you the entire adjacency matrix. You can see the whole thing. That's the input. But emergent from it is this very large operator, which encodes the topology of the graph. That's the key.
Just to put this in context, so the previous result of Tamara and this was, they also had KMA 100, but for
right. Yeah. So so the previous paper, which is also my co-author was also an author of, showed hardness for a different problem to the one that's inside QMA. So this is the problem that's inside QMA, and this is the one we tried to show. Or yeah, we tried to show is QMA hard. The one that they showed as QMA hard is this without this condition of being sufficiently far in the no case. So then it could be, much harder. In fact, I actually think that probably that problem is p-space. Yeah. So it's sort of if I get rid of this condition, it ceases to be quantum mechanical because I can't detect this exponentially small eigenvalue with a phase estimation. So that's why it was sort of not fully completing the story and not fully convincing. Yeah.
Why do we need the graph to be vertex bending?
Yeah, so I'll talk about that hopefully if we have time at the end. That comes up later. But it doesn't ruin the. I'll just say it doesn't. It's just sort of making the input more general. It's still in QMA, and it's still a succinct input.
If you had edge weights, then probably you cannot get cancellations.
Yeah, so it turns out the right way to weight these things is to weight the vertices because because then the weight of a simplex is like the product of the weights of the vertices. Yeah. Okay, so now's a reasonable time to mention this connection that I talked about before with supersymmetry. So there's a sort of dictionary you can write down between a supersymmetric quantum system and homology. So the Fock space of a supersymmetric quantum system you identify with the chain space. And I guess the different dimensions of the chain space correspond to different particle number sectors of the Fock space. The so-called supercharge turns out to be equivalent to the boundary map. The Laplacian object the self-adjoint operator, is precisely the Hamiltonian of the supersymmetric quantum system. And if we talk about the homology of a Clique complex like we are doing here, this corresponds to a certain class of supersymmetric quantum systems called the fermion hardcore model, where you have a graph and fermions live on the vertices of the graph, and they sort of aren't allowed to be on two vertices of an edge because they sort of repel. I guess, this is all I'll say about the connection with supersystems.
Is the last point.
Oh, good point. Yes, true. Sorry, this should be, sorry, the bottom row is, thank you, the wrong way around.
Can you say a bit more about what the Hamiltonian is in the supersymmetry? Like, what does it correspond to in terms of fermionic interactions?
Right. I mean, the way I think about it is it's precisely this Laplacian object. So you sort of have a supercharge Q, they call it usually, and like the supersymmetric Hamiltonian is like Q dagger plus Q dagger Q. That's sort of how they define it, and then that is precisely matches this definition we have for the. Yep.
Is it to implement unitary that represents the Laplacian?
Yes. So we're given. I mean, we have. It's a big matrix, and we have efficient sparse access to it. So we can, import any Hamiltonian simulation algorithm you like, and you can do Hamiltonian simulation, and then you can do controlled Hamiltonian simulation, phase estimation, anything you want.
So in the no case is the promise of the second half of the technique not
Yes.
You only need that for the
Yes, that's a good point. Yes. So we're not. It's just for the case. Yeah. Thanks.
Why is your talk not about binary computing codes? Like, why they don't show up in this hardware?
Okay, so you're asking here. Yeah. Okay. So there's a few differences. So in quantum error correction, these spaces are not exponentially large, right? They're sort of. This is like how many bits you have in your code or something.
Oh, I see.
Yeah. And it's also over F2 usually, and I think it's just not a comparable setting, I guess. I mean, yeah, it's like in error correction, you have these spaces explicitly. Right.
Yeah, instead of the underlying graph. That's it.
Yes.
I mean, the sequence for error correction is very short, right? I mean, you typically don't go to very high dimensions.
Yeah. Also, yeah. Okay. So let's return to the original sort of motivating topological data analysis and ask, okay, so what are these algorithms doing? What are these quantum topological data analysis algorithms doing? And we can now very simply say what they do. So they exploit the ability to do phase estimation on this Laplacian. That's how they work. So you can then ask, can we dequantize this thing? So phase estimation on an arbitrary quantum Hamiltonian, you cannot dequantize. That's sort of, a BQP complete thing to do. This is all sort of roughly speaking, I guess. None of this is fully rigorous, but so if you were to dequantize this quantum TDA algorithm, you would need to exploit some special structure that the Laplacian has that is not present in generic local Hamiltonians, generic quantum Hamiltonians. So this result that the ground energy problem for this Laplacian is QMA hard should tell you that there is no exploitable structure. These things can be as hard as general quantum Hamiltonians. So it's evidence that we cannot dequantize these TDA algorithms, and there is genuinely something quantum going on. Okay, so the rest of the talk is about how to show the hardness, but I realize that I'm basically out of time, so.
I think we're interested in taking like 5 more minutes.
5 more? Okay.
I think we can take 5-10 minutes.
Okay. Let me see what I can do. Okay, so I'm in a bit of a dilemma because the construction is sort of the ideas in the construction actually just sort of are very similar to the previous paper, and there's a new aspect, which is this use of this thing called spectral sequences, but it's sort of hard to get there without going through the. So maybe I can just for 5 minutes talk about spectral sequences at like a very high level, and possibly no one will understand anything. But is that? Yeah. Okay.
1 minute tells how the encoding works.
Which encoding? Sorry. Oh no, but that's the one that's what I was going to skip.
Oh, you're gonna skip?
Yeah, I was. Yeah. I mean, otherwise I'm going through the whole thing, which will take too long. So, okay. So I need to go back to this vertex weighting thing. So we're going to weight the vertices of the graph. This is just making the input model more general. And this doesn't change the topology of the graph, but it does change the Laplacian. And how that appears as this adjoint thing is with respect to an implicit inner product. And the weighting of the vertices will weight this inner product. So that's why the Laplacian becomes different. Okay, so that's the weighting. And what we're going to do is we're going to, so I realize this will make no sense, but okay, roughly how the construction worked is that we want to reduce from a Hamiltonian problem. So we want to start with a Hamiltonian problem that in the yes case has a 0 eigenvalue, in the no case has some positive. Maybe I'll just go to the slides actually. In the no case has some positive ground energy, and we want to output a graph such that in the yes case it has a hole, and in the no case it's far from having a hole. So we're going to do this by starting with I'm going to skip all this, starting with a complex which has a lot of holes, like 2 to the n many. So this is like the qubits without any Hamiltonian. And then for every Hamiltonian term, we're going to glue in a gadget which is going to implement the Hamiltonian term. So the qubit vertices, we're going to weight with weight 1, and the gadget ones we're going to weight by some lambda, which is small. And the reason we do that is because we want the gadgets that we glue in to act as perturbations on top of the qubits. So now to the main difficulty in this hardness proof is to show that this gap carries over, right? So the reduction satisfies this property that if there was a lower bound on the eigenvalue of the Hamiltonian you start with, that there's also a lower bound on the Laplacian. So for this, we need to do perturbation theory basically on this Laplacian in this lambda quantity, because we want to understand how does the ground space, what does it look like when we add these perturbative gadgets which implement the Hamiltonian in this topology. So the way we do this, so you could try to use standard perturbation theory, but this would be like impossibly difficult because we need to go to something like 14th order or something crazy, right? But because there's all of this nice topological structure, we can use this tool from algebraic topology known as spectral sequences. So the ground spaces of the Laplacian to first, second, third order in perturbation theory form a sequence of spaces where if I go to infinite order, I get the true ground space, right? Similarly, from this weighting, we get a filtration, and from the filtration, we get a spectral sequence of spaces, which is an algebraic sequence of spaces which also converges to the true homology. And there's a paper from the 90s which tells us that these two sequences of spaces are in fact isomorphic. So the perturbations of the ground space of this Laplacian are isomorphic to this sequence called the spectral sequence, which is much more algebraic and easy to compute. So you can turn this difficult topology and analysis problem into a much easier algebraic problem where you just sort of computing these algebraic spaces by taking iterative, how it works is you have these pages, and to get the next page, you take the homology of the previous page, and this page, the successive pages correspond to the various orders in perturbation theory. So I realize that might have made no sense, but hopefully I just gave you a high-level picture.
So if you're doing perturbation theory, how do you get QMM1 hardness? Usually QMM1 hardness is not perturbation theory, doesn't usually give you QMM1 hardness.
Right, so we're going to use this in the no case. So in the yes case, there's a 0 eigenvalue, and the construction, by construction, has a hole. So this tool is for the case.
And this gadget doesn't affect the yes case.
No.
It only affects
Yeah. This we only need this in the no case. Yeah. So it's like showing that there is like a reasonable gap of this. Like the complex we end up with is sufficiently far from having a hole. Yeah. Okay. Yeah. That's. Oh.
So you've given a Hamiltonian, you give a graph, and K also is the parameter for your problem, right? So how do you decide what is the K complex that you need to look into?
Oh, as in what is K?
Yeah.
Yeah, it will be something like 2n minus 1 or something where n is the number of qubits. Yeah. Okay, so with that, I'll conclude. And yeah, if there's anything to take away, it's that this Laplacian is an interesting operator which encodes topology, and it's a sparse matrix that you can get efficient access to. So all of the sort of properties that we need for quantum algorithms and quantum complexity, and it corresponds to a supersymmetric Hamiltonian. And then, since this is a PCP workshop, I guess the last point is about PCPs. Maybe because it's a QMA hard discrete sort of combinatorial problem, you can hope to sort of do these graph gadgets to amplify the gap, etc. But very much unexplored. Okay.
Yeah, going into this question. So, like, yeah, the thing I think you skip like the reduction. Do you pay t squared if your QMA1 verifier is p8 or like? You're paying the same thing as that construction?
Probably even worse in our construction.
Okay.
Yeah. In terms of the gap, I think, yeah.
what's the notion of the qubit in your construction?
Right. Yeah. So in the construction, we'll make a qubit, or in the reduction, you mean, by this is what a qubit looks like. So we have this bow tie graph, and the one homology, it has two loops, right? So it has two holes in it. We identify one of the holes with the 0 state and the other one with the 1 state. And this is sort of what one qubit looks like in the reduction.
And n qubits will include the n holes.
Yes. So to get n qubits, you take n of these things and sort of tensor product them together to get some crazy thing with like 2 to the n many holes.
Do you think QMA is somehow related to homology problem?
Sorry, say that again?
Do you think QMA is somehow related to homology problem? So do you think it's QMA hard, for example?
Oh. So the reason why QMA1 is more natural is because this Laplacian is sort of like a PSD operator, and then if it has a 0 eigenvalue, that's when there's a hole. So it's sort of unclear how to, yeah.
I have a question about this lambda weighting gadget. The two questions. One is, does it retain the supersymmetric structure? And second, for the, not the ground state, but the higher spectrum of that Hamiltonian or Laplacian, is there any level crossing as you change lambda? Not necessarily 0, but around, when you move lambda away from 0 to some large value?
Okay, so for the first question, the answer is yes. For the second question, I'm not sure I know what level crossing is.
So eigenvalue is just close.
Yeah, I think so. At some point, yeah. So like as I turn lambda from 0 to non-zero, sort of these degeneracies will split, just like in perturbative gadgets. And that's the sort of regime that we want to be in, where we can sort of analyze the subspaces within each thing without them sort of mixing up. But then at some point, they'll probably start getting mixed.
Yeah, of non-zero eigenvalue taking cross.
Yeah, I think that probably is.
So coming back to the field, you chose C because you wanted to represent amplitudes for the quantum case.
Sorry, say that again?
You chose complex
Hmm.
because you wanted to represent the superposition. For
Yeah.
But if you say chose the real, would you get a kind of a lower class for complexity?
That's a great question. So I think it won't affect the homology if you switch. Maybe, yeah, I think if you switch complex for reals, I think the homology is unchanged.
Yes, but would you be able to still get the reduction from the Hamiltonian?
I see. Okay, let me think about this. I guess it's still probably one way is still, I'm trying to think about it, but like probably it's still, maybe you can't simulate the Laplacian anymore if it's, yeah, it's a good question. I need to think about it. Yeah.
Great. So thanks to Robbie for a great talk. And lunch till 1 p.m. We'll see you back again at 1. Quick announcement. Please send us, please nudge us if you have open problems to share, and let either me or Bill know, or send an email to us.